Welcome to Talk 10. Today we're stepping back from specific statistical outputs and focusing on study design, specifically the two most common observational study designs you'll encounter in veterinary literature: cohort studies and case control studies. These are the backbone of much of what we know about risk factors, disease associations, and prognostic factors in veterinary medicine. They're also where the most important sources of bias live. Understanding the architecture of these studies, what direction they run in time, what they can and cannot tell you, and what biases to watch for is foundational to reading the results section with appropriate skepticism. Let's get into it. Here's our roadmap. We'll start with the conceptual landscape, then work through each design type and spend significant time on bias, because that's where observational studies live or die. We'll close with the Bradford Hill criteria, the framework for deciding when an observed association is strong enough to consider causal. This is what separates careful clinical reasoning from jumping to conclusions. Let's start with the key distinction: observational versus experimental. In an RCT, the researcher decides who gets the drug. Randomization makes the groups comparable. In an observational study, the researcher simply watches what happens to animals who, for reasons of their own or their owners, received different exposures or treatments. This distinction is everything. Without randomization, the groups being compared can differ in many ways beyond the exposure of interest. Those differences, confounders, can create apparent associations that are entirely spurious. Observational studies are not inferior to RCTs for every question. Many important clinical questions can never be ethically answered with an RCT, but they require more careful interpretation. Cohort study is the closest observational design to an RCT in terms of temporal logic. You identify two groups at baseline, exposed and unexposed, before anyone has developed the outcome. Then you follow them forward and count who develops disease. This temporal sequence, exposure before outcome, is critical for causal inference. It's also what allows you to calculate the true incidence rate and the risk ratio directly. If 20% of exposed dogs and 8% of unexposed dogs develop the outcome, your risk ratio is 2.5. Prospective cohorts measure exposures prospectively, which reduces recall bias, but takes time and money. Retrospective cohorts use existing records, so they're faster, but you're at the mercy of how well exposures were recorded in the past, which introduces recording bias. Case control study flips the direction. Instead of starting with exposure and following forward, you start with the outcome, cases, and compare their past exposures to a control group without the outcome. This makes case control studies very efficient for studying rare diseases. If you wanted to study risk factors for canine mesothelioma using a cohort design, you'd need to follow an enormous number of dogs for years to accumulate enough cases. A case control study lets you start with the cases you already have and work backward. The cost is the OR-only constraint. Because you've selected your study participants based on outcome status, you can't calculate the true disease incidence in the population, so you can't calculate a risk ratio. The OR approximates the RR when the outcome is rare, but not when it's common. Control selection is where case control studies most often go wrong. Controls need to represent the same population that would have become cases if they'd developed disease. Hospital-based controls, convenient but common in veterinary medicine, may differ systematically from community controls. This is the defining challenge of every observational study, and it's worth spending real time on it. Selection bias enters when the animals who end up in your study are not representative of the population you're trying to study. In a hospital-based case control study, your controls are animals that happen to present to a referral hospital for something, which makes them systematically different from the average dog or cat in the community. Information bias is about measurement. In a retrospective record review, how consistently was the exposure recorded? Did different clinicians document the same thing the same way? In a questionnaire study, do owners of dogs with cancer remember past exposures better than owners of healthy dogs, inflating the apparent association? Confounding is the variable that's associated with both the exposure and the outcome. We covered this in depth in talks 5 and 9. Multivariable analysis can adjust for known confounders, but unmeasured confounders remain a limitation of every observational study. The key habit for any reported association, ask what bias might be operating here and in which direction would it push the estimate? Would it make the association look stronger or weaker than it really is? The Bradford Hill criteria, originally proposed in 1965 for human epidemiology, are the framework for deciding whether an observed association is strong enough to warrant a causal interpretation. They translate directly to veterinary medicine. Temporality is the only one that's truly non-negotiable. If you can't confirm that the exposure preceded the outcome, causation is off the table. This is why cross-sectional studies are inherently limited for causal inference. You can't determine which came first. Strength is about effect size. A risk ratio of 8 is hard to explain away with bias. A risk ratio of 1.2, possibly real, but could easily be a residual confounder. Consistency across multiple independent studies, ideally in different populations and different study designs, is the most powerful evidence for causation short of an RCT. Dose response is compelling biological evidence. If risk increases as exposure increases and decreases when exposure decreases, that's hard to explain with confounding alone. Let's work through this case question together. It's a realistic and clinically relevant scenario. You're looking at a case control study of lawn herbicide exposure in transitional cell carcinoma in dogs. OR equals 3.4, confidence interval 1.7 to 6.8, doesn't cross 1. Statistically significant. The association is moderately strong. An OR of 3.4 is not trivially dismissed by bias. Let's apply Bradford Hill. Strength, moderate to strong. Consistency, is this replicated? This has actually been studied multiple times in dogs with similar findings, which increases confidence. Temporality, case control studies can verify this where owners asked about exposure before the cancer was diagnosed or after. If after, recall bias is a concern. Plausibility, aromatic amines in herbicides are known bladder carcinogens, biologically plausible. Dose response, not assessed in this study. A gap. Unadjusted confounders, indoor versus outdoor time, is a big one. Dogs that spend more time outdoors have more herbicide exposure, but they also have more sun exposure, more physical activity, and different microbiome profiles. Outdoor time itself could be an unmeasured confounder. The Scottish Terrier finding is interesting, suggests a genetic susceptibility that may interact with herbicide exposure. This is worth investigating, but doesn't confound the overall association unless Scotty ownership correlates with herbicide use. Bottom line, this is a moderately compelling association supported by biological plausibility and some consistency across studies, but short of proving causation. Confounding by outdoor time is a meaningful limitation. The evidence is sufficient to counsel clients about minimizing herbicide exposure, especially for at-risk breeds, without claiming we've proven causation. To sum it up, cohort and case control studies are the engines of veterinary epidemiology. Knowing their direction, forward versus backward, tells you what metrics they can calculate and what their key vulnerabilities are. Bias is the defining limitation of every observational study. Build the habit of asking, what bias could be operating here? Could it explain the result? In which direction would it push the estimate? And always apply Bradford Hill when an observational association is being used to make clinical recommendations. Temporality, consistency, strength, and biological plausibility. If most of these check out, the evidence is building. If only one or two do, hold your conclusions loosely. If you'd like more short, clear epidemiology lessons, go ahead and subscribe before you head out. And if this video helped, a quick like tells YouTube to share it with other students who might need it. And if you want help staying focused on what really matters in vet school, you can also check out my hub channel, Surviving Vet School. Everything there is designed to make the hard stuff feel manageable. Thanks, and see you next time.